talk by Ferenc Bench on Christoffel-Darboux type identities for the independence polynomial.
Thanks. First of all, I would like to thank the organizers for this really nice workshop. I would like to speak about the independence polynomial and some combinatorial and algebraic aspects of it, which could or might be help us to understand the roots, or at least we are trying to understand what's the connection between the structure of the graph, for example, and between the roots. And so first of all, I will use IGX for the independence polynomial for today. I will denote by IGX. We have the family of independent sets F in the graph G. So just to be sure that we are speaking about the same partition function, if this is the graph, this is my polynomial. Okay, so there is there is exactly one empty set which is independent. We have 5 one-sided independent set, and there is exactly 3 non-edges of this graph. Okay, so we are some motivations for the independence polynomial is that basically we like it because it's, for example, it is the partition function of the hardcore model, right? Also, we really like it because it somehow help us to understand how far we can extend the lowest local lemma by keeping the same dependency graph. Also, it could encode various combinatorial objects from the fields. So, for example, largest independent set, largest matching in the graph, all the matchings of the graph, or all the click coverings of the graph. So all of these can be somehow encoded as an independence polynomial, and so on. We could make it. So the next thing what I would like to speak about is Christoffel-Darboux identities. These identities are well known in the theory of orthogonal polynomials. So what is this? So whenever we have an orthogonal sequence of polynomials, we can always find positive real numbers, such that this quite long but useful identity holds. And this is called the Christoffel-Darboux identity. So I don't need that what is exactly the orthogonal polynomials. I just want to give you the flavor of it, that how can be useful this long expression. Okay. So for example, this kind of expression could be really useful in order to find roots, proving that the orthogonal polynomials has only real roots, for example. Okay. So let's try to prove it. Okay. So if we are believing that this identity holds, okay, what would be our strategy to prove it? Let's take the smallest counterexample. Okay, we take it, and then choose a complex root of it, right? Which witnesses the non-relatedness. Okay, and then what to do? Let's use this formula and plug xi and xi conjugate at x and y. Okay? What will happen? On the left-hand side, we will have this will be 0. This will be 0. Therefore, the upper part will be 0. Since we choose really complex roots, so x minus y will be a non-zero number here. So this left-hand side is a big 0. And what's happening on the right-hand side? The right-hand side, what we will see is the conjugate of the same quantity. So these will be lengths of complex numbers. These are positive coefficients. So the right-hand side is a positive number. So we get the contradiction. Yeah, and we didn't check the base case of the induction, but this is the moral feeling how to prove such a thing. So and later on, Chris Gottsill generalized and introduced identities for matching polynomials, and he called them as Christoffel-Darboux identities, because somehow there are this identity can be found among the matching polynomials also. So I think this is how he take this name. So he introduced a bunch of new identities for matching polynomials. And what I was able to do is to generalize or found some similar identities for the independence polynomial. So what is it? So we can take this expression, which could be quite familiar from the first talk. So this is something like correlation, right? So we are deleting the vertex u and then deleting v, the minus without deleting and then deleting u and v, right? So the left-hand side is this correlation, say it, and what is true is that this thing will be, as I said, long formula. So this is a summation over all induced bipartite subgraphs of G, which contains u and v, okay? And I denote by this bracket the closed neighborhood of the subgraph, okay? So it's quite similar in some sense that on the right-hand side we have something to the square, or this is right now, it's not a two-variable identity, it's a one-variable identity, but it's quite similar. So from here, we can, for example, prove that if we are so lucky that the distance of u and v in any bipartite induced subgraph is the same parity, okay, which is the case in a bipartite graph. So in a bipartite graph, any induced subgraphs, u and v will have the same distance up to parity. Then we could get this correlation. So we get positive correlation and negative correlation for all positive x, what we use.
In your theorem, is there an assumption that G is bipartite?
No. Here I have assumption bipartite. So when we are using this theorem for a bipartite graph G, then this DHUV will be always the same.
So how does bipartite occur in your right-hand side? Could you say a word about this?
On the right-hand side here.
Well, your set is BUV is a set of bipartite connected induced subgraphs. So I'm just wondering about that. The third line
yeah.
says bipartite.
Yeah,
how
bipartite.
does this occur? Why?
What's the reason?
Oh, why is that the reason? Yeah. So so the reason is that if you consider, so let us imagine we have two independence. So we have one independence polynomial and we take the square of it. Then what will happen that we can imagine that each when we are taking the product, we will take a monomial from one side and from the other side. We can think as the independent sets also. So in some sense, the product of two independent polynomial will be a partition function of such a colorings where two colorings are independent sets. In other words, if we project it down, it's bipartite graphs and induced. So this is how they come into the picture. Yeah, so this is what I basically try to start it to prove here. So,
I have
yep.
a question. So Baudelaire also had some Christoffel-Darboux identities. So what's different with your?
He just used it for clove-free graphs, I think.
So, okay, so his identity is only for claw-free graphs?
Yeah.
Okay. Then it's a big difference.
Yeah, so in claw-free graphs, it will become much nicer.
Yeah.
Because this set will be much nicer. So the proof, how does it look like? So we can define configurations as bipartite graphs in the original graph, and we will, for each configuration, we will give them different weights depending where they are coming from. Okay, so if someone is came from here, it will get some weight, and so basically imagine that we take two independent sets from this graph, and then their disjoint union, and this is H. And then we can just calculate what is the number of isolated vertices of H other than U and V. What are the connected components of H of size at least 2, which is not U, not V. Okay? And then we can define 4 sets, which so the first 3 will partition C, depending on U and V is in the bipartite graph or not, or exactly one of them is in the graph. And the third one is a subclass of the third. The fourth is a subclass of the third, where we put the condition that U and V should be in the same bipartite component. Okay? And now what we can do is that we can express using these classes of this product. So it's quite technical, but this is the summation what we will gain for G minus U, G minus V. And if we do the same calculation for G and GU minus V, we get the same terms here, except the last one. And what is this last one? That H is a bipartite graph where U and V is in the same connected component, and their distance is even. This is here, and in the previous it was odd, the distance. So this is why we will have in the formula -1 to the distance of U and V plus 1. Okay, that will decide the sign. And all of these will disappear. Okay, so that was the idea behind the proof. Yeah, I have to mention this is a simplified proof due to the idea. So there is another formula what we can write up. Now I write it immediately, the second line. So this is the expression. So here we have all the bipartite connected induced subgraphs of G. This is the summation. And we will have here P and R. They are the cardinality of the color classes. Okay, P is one side, R is the other side. Okay, and it's really symmetric in changing X and Y, so it will work. Okay, so and now I'm stating that if you just believe in this formula, okay, we can give a short proof for the claw-free to the Chudnovsky-Seymour theorem, which says that claw-free graphs has rerooted independence polynomial. And why is that? So first, I'm saying we will use this formula. So what we have to understand is this set. So all induced connected bipartite subgraphs of a claw-free graph. Since claw-freeness is a induced, the claw-freeness of, so induced subgraph of a claw-free graph is claw-free. That means that we are looking for bipartite connected claw-free graphs that are nothing else but even cycles and passes. Okay? But in an even cycle or in a path, the difference between the two color classes is at most 1. Okay? So this whole thing can be written in this form, okay? Where R is the smaller cardinality of the color class, okay? And I just divided by y minus x to make it more nicer. And now we can use almost the same argument as before. So assume that we have a root, a complex root, xi, and put xi in x and put xi conjugate in y, then the left-hand side will be 0.
So on the slide in the previous page, there was some plus minus 1 term that disappeared with this formula.
Yeah, here so it's not disappearing, it's appearing here. It's because now we have two variables. Now it will separate them. So at there we had only x's, and
so they're kind of the degenerate x equal to y version of this.
not. So if you write x equal y, then you get 0. So
Sure, but if you take out the root,
they are just related. So you can derive from one to the other, basically. Yeah. So this is the short proof of Chudensky-Seymour theorem. But what we...
Yeah, I have a question. So is here sort of untangle Chudensky-Seymour proof, so it's completely different, or it's somewhat... they also argue sort of interlacing.
They are using interlacing polynomials, yeah.
So you're sure it's completely different, right? So it doesn't have this some form, some other form.
Even the length is different. This is one page, the Chudensky-Seymour is that page.
No, I understand that. Okay.
It is completely different, but it's the same proof as Baudelaire says, right?
As what?
As Baudelaire, he has this same proof. But is your identity the same when it comes for claw-free graphs now?
So when he does this, he creates some bounds on depending on the I cannot recall it exactly right now, but he uses he creates some bounds of it. So if we know that the imaginary part is at least, we know what is the imaginary part, then it will give us a lower bound on, I think, in this expression or something like that.
So this is not the identity that he has for the
for the claw-free graphs is the same. Yeah.
So this is a proof.
Sorry?
So then is the sense.
It essentially is the same, yeah, but he somehow, I don't know, he go in a different way.
Right?
Yeah. And you know, so this statement holds in multivariate sense also, and I think Jonathan, you generalize this for multivariate independence polynomials, and you show that they are same phase stable.
Yeah, I mean, I wasn't the first one to. Me and Nick
Yeah.
weren't the first to show that,
But yeah.
we give some proof of that.
Yeah, but this holds in multivariate cases, I think. Yeah, so, and I think this is what's happening there also. This is my feeling, so. Yeah, so we can wonder what we really used in the Chudensky-Seymour theorem, and it turns out that basically what we really used is this difference between pH and RH. What was that maximum, okay? So the maximum difference between the two color class, okay? And it turns out that if we just really use this bond, this kappa, I don't know any name for that. So what we can state is that whenever we have a root, it cannot be lie in the p divided by kappa sector. Okay, it's basically the same proof as the previous. Okay, there kappa was exactly 1, or at most 1. So pi divided by 1, so we get back exactly the same statement what we desired. So this is a sector freeness result what we can obtain from this formula. And we can wonder what kind of graphs can be can have bounded kappa. Okay, so the first class is clearly the at most one. It turns out, yeah.
Why is it hereditary?
Sorry?
Why is it hereditary property?
Because it's about induced graphs. So so B was the set of all induced bipartite connected subgraphs. So if I take a smaller graph, this set will be just smaller. So the maximum, it could be only smaller. Okay. So if I say at most kappa, then it is a hereditary graph. So what are these classes? So we can ask for 1. This is what we saw. This is the Clofree graphs. You may wonder what is 2. And it turns out these are the graphs that doesn't contain even length double fork. Okay? So this is an infinite list of graphs. I don't know any name of them. I don't know any subclass of it. But these are the forbidden subgraphs. K can be at least 0. Okay? So the K14 is there. So this is the forbidden subgraphs now.
So there is a path between this?
Yeah, induced path of length 2K. Yeah, this is an induced graph, so yeah, the dot's missing there. And also we can ask for 3. Here the family is 2 parameterized, so this is one guy, and this is the exceptional one. So these sets, and I don't know how far it can be continued, but yeah, this is like a question for maybe for the audience that do you know any nice classes which is contained here, or we can say any boundedness. So, but on the other hand, it raises the question that really the close causes this distribution of the roots. So if I have more close, I will be not that many real roots. So I will be further from the real line. Okay, and the question is somehow settled. So basically, we have to look the path tree, the self-avoiding path tree of the graphs due to Scott, Soka, and Weitz. And this will solve the problem because we know this identity and we really like it. But the question here is that can we give more insight of this ITX? Okay, so the independence polynomial of the self-avoiding walk tree. And it turns out that yeah, it has some nice properties. First of all, its maximum degree is at most the maximum degree of the original graph. Fine. But it's also true that we can identify a subtree of the self-avoiding walk tree such that whenever we take the independence polynomial of the complement of this subtree, we can use polynomial division, and we can get back the original independence polynomial. So the whole independence polynomial divides the independence polynomial of the self-avoiding walk tree, independently how we create the self-avoiding walk tree. And also what's true is that in this case, the T is a product of induced subgraphs, independence polynomials. So it's more true, so not just divides it, but all the factors are induced subgraphs. So how can we use this? So for example, the starting graph is a Clofree graph, okay? And we create any self-avoiding walk tree of it. Then the result will have a tree, okay? And we know that the tree independence polynomial will be the product of induced subgraphs of the original graph. But a Clofree graph has Clofree subgraphs only. Therefore, the independence polynomial of the tree will be rerouted also. So now it shows, and you know, whenever we start from a Clofree graph, we create this tree, it will have a bunch of claws. Okay, so really like we can have a lot of claws, but still rerouted graphs. Okay, and this is basically in some sense it's used on Monday's talk, right? Yeah. So we are taking passes where we connect two vertices if their distance is at most k. What you gain is trees, basically, that are rerouted. Okay, another application of that, whenever we have two graphs and they have the same self-avoiding walk tree and one of them was claw-free, then automatically the other will be rerouted. Okay, so it could happen. There are examples that can be proven this way. And also another really important property of this independence polynomial and the self-avoiding walk tree, which is the following, that whenever we take all the roots of the independence polynomial up to a degree d, okay, this is a large set of roots, and we can ask how is it related to the roots of all the trees, okay, with bounded degree condition d. Clearly one contains the other, but it turns out because of this divisibility relation, these two sets is exactly the same. So why is it good for us? Because there are techniques to find zero-free regions for the hardcore model. And usually when they are doing this kind of recursion thing, there is always a last step. A last step is to handle the trees when the root has exactly d child. Okay, so usually all the proofs works nicely till the point that everyone has exactly d minus 1 down children. Okay, but sometimes we have to solve the cases when the root has exactly d child, but you know, in a tree we can always choose a vertex which doesn't have exactly d neighbors. It has a leaf at least, or two. So we can hang the tree from the leaf. Okay? So in other words, if we are aiming for a root-free, so saying that lambda is not a root for any graph of degree at most d, it is equivalent to the fact that we can find a set which contains 0, doesn't contain -1, and it's invariant under this map, okay, where we are specifying only d minus 1 variables. Okay, and this is enough to check. We don't have to wriggle one more step. And I think so. This is how far it goes. So this is the Monday's result about zero freeness of the hardcore model due to Monday. So so we have the Shearer region here, the biggest disk, and here the f lambda what they used was disk. Then it was shown by Rechts and Peters that zeros are accumulating to this blue curve. And they also showed zero-free region, this brown one. And they showed zero-freeness around the real axis till the boundary. Then with Chikvari, we were able to show that there is no roots in a bigger region, this pink, which contains the first region of Rechts and Han. Here we used trapping region circular sectors. And recently on, and then Piotr proved that, this kind of, there are fangs So there are curves which cutting into UD. And sorry, these are not precise image, so I just draw some curves there. So anyway, to these curves also we know that there are zeros that accumulates. Okay, so there are infinitely many roots inside this big cardioid. And on Monday they said that yeah, they computationally they can show that there is a nice region here which is 0, 3. And what they used, trapping region there is some kind of sequence of curves. Yeah, same. Yeah. So this is what they proved, and I think quite recently you can say more somewhere here.
Keeps growing. Yeah. There's
something here. Yeah.
We don't know exactly what it is.
Yeah.
Disconnected from the rest, or?
No, connected.
Connected.
There's some natural extension of this that we have to get a better handle on.
Yeah. So, thank for your attention.
And questions?
Just a couple of questions. Could you tell us or remind us if this vertex independence polynomial satisfies deletion contraction? You know the deletion contraction formula?
Deletion contraction formula for.
Well, you.
What's the
chromatic
recursion
polynomial.
for the
Sorry?
What's the recursion?
What are the recursions? Okay, sorry. Deletion contraction. Okay, yeah. So IGX in one variable. This is IG minus you delete the vertex. Okay. So you are counting all the independent sets which not containing U. Then you have to count all those who contains U. Whenever U contains U, you have an X, a multiplier, and then you have to take the close neighborhood of U out of G, then X.
So it does satisfy deletion contraction.
Deletion contraction.
It's not deletion contraction.
It's not
it's a recursion, so yeah.
Well, it's almost deletion.
The word contraction is a bit misleading.
Right, it's almost deletion contraction. So my question is.
There is no contraction.
Right.
So it's deletion.
It's deletion and deletion.
The edge independence polynomial satisfies deletion contraction, but this one satisfies like this weird thing. Anyway, my question is, just because you have some form of deletion contraction, say you have this whole class of polynomials that would meet just this requirement, could you derive your Christoffel-Darboux from there? You can derive Christoffel-Darboux for orthogonal polynomials from the recurrence relation.
Yeah.
So hence my question.
Yeah. I don't know.
It could be very interesting to try.
Yeah. I never thought about that.
And may I make just a remark on your sectors that you're obtaining? This might be completely irrelevant, but two of my co-authors and I have a paper where the sectors arise from matrices, very specific structure, which we call generalized Hurwitz matrices. Mm-hmm. And if they are totally non-negative, then this regions, the zero-free regions, will be guaranteed. So that's the subject of that paper. So again, I don't know offhand if there are any natural matrices that will be leading to total non-negativity, but maybe there are sort of lurking in the background.
Yeah, good. That sounds interesting. Yeah.
Other questions or concerns? If not, let us thank the speaker again. And we